Hello, we were talking about the scientific method yesterday, and now we're going to be talking about two different concepts, samples versus population. So population is basically the who or what you are studying. And a sample is like a little piece of it, kind of like when you go to the grocery store and they give you like a little sample of the cake that they're offering. So a population would be like all the cakes that they sell at the store, but a sample would be like a little piece of that. So then here we have a sample. So the population is the thing being studied. And then a sample is a representative piece. Like, okay, well, yeah, the piece would have to be representative. How do we know it's going to be representative? Well, it needs to be an accurate representation. And I'll go into an example in order to see if a sample or if a sample is a proper sample of a population. Okay, so let's say that we were doing a study and we wanted to survey people who were between the ages of 18. So our target population are people 18 to 24 years old. And we're specifically targeting people who live in Texas. It would be very difficult, not to mention expensive, to survey every single 18 to 24-year-old in Texas. So instead, you will interview some 18 to 24-year-old people in Texas, and then based on the findings from that smaller group of people that represent the bigger thing that you're studying, then you can make some conclusions about that. Now, so you could say maybe do a study of 500 people that are 18 to 24 years old in Texas. You could even do it as much lower, maybe like a group of 100 people, but you have to be more mindful of all of these little variables. Like, okay, so 18 to 24-year-olds, are these people who have a job, don't have a job? You're going to try to make sure that the characteristics of your sample are the same as your population. So there's going to be like other things that are part of that. So let's say that they have work part-time. So if you're going to be focusing on people that work part-time, you're going to want your sample to also be people that work part-time. It's like the saying goes, you want to compare apples to apples. I do want to also point out that when we are making a population and a sample, we have to make sure that we don't have like too much of a bias. So let's say that we weren't being as strict enough with people working part-time. in our sample, we might get people who are not employed or too many people who all work full-time jobs. So what we're going to be trying to use for our study isn't going to work out. It's not going to match. And that's why having like a bigger sample size, so like including more people in the study, allows you to have more randomization. So increase sample size, you increase randomness, and the more random something is, the less likely it is to be biased. We're not going to eliminate 100% bias. I mean, we'd have to like be increasing like almost to infinity, but just we want to make a generalization. A generalization is something that you make in general. It doesn't have to be like 100% fact. If you realize studies aren't all about 100% things being 100% effective, it's like saying, with this medication, we've seen 85% increase rate in healing time. It says it was effective 85% of the time, it wasn't effective 15%, and then like what they determined to be the scale of effectiveness in the study is something else as well. So now we're going to be talking about whether a conclusion can be judged with a scientific theory. And based on that, you need to be able to look at the data that are going to be presented. So let's say I draw a graph right here. And I'm going to say that this is the rate of rates of infant mortality between 1940 to 2009. I did not like come up with this off the top of my head. I know the topic does sound a bit morbid, but if you look at the trend in the data, it actually finishing drawing out the chart. And this graph is from the CDC. And it's saying that between 1940 to 2009, there has been a decline in rates of infant mortality. So in 1940, there was around, let's say, 45 deaths for every 1,000 babies that managed to be born. But as time went on, we are seeing that there's less babies dying for every baby that is being born. So that's a very good thing to happen. We want less babies dying. So more babies are surviving the childbirth process. So the trends here, the conclusion that we can draw based on this data, and this is how the GED or high state might ask you, like it might give you a chart or data and say interpret the data, and you have to draw a conclusion. So our conclusion based on the data is the rate of infant deaths in the United States has declined drastically between, and actually let me just draw here. Ignore these little chicken marks. So we're seeing that here is where there was like the most drastic change. Like it's much steeper. If you remember from math, we were talking about slope. Here, there's not much of a change. Like it's only goes down a little bit, whereas here it went down drastically. So we can say the rate of the infant deaths in the United States has declined drastically. We know that there's less babies dying. And we can actually be more specific by saying between 1940 and 1960. So we were just being extra specific. Now with the with the answer choices, you might have to pick between like different answer choices, and they may be very similar. It might say instead of rate, instead of decline, it might say increase. So just be very mindful when you're eliminating your answer choice. So here what we did is that we made a conclusion based on current data. Something else that you might do, excuse me, with data that you're already being presented is that you might have to make a prediction. So it's like, all right, we're seeing that it's decreasing. If this keeps on happening, what do we expect to happen in the future? So if we're expecting it to just kind of continue in a downward, the trend, seeing the trend go in that direction, we're going to expect for there to be, there's an answer choice. If they're going to ask us, do you think there's going to be 50 deaths per 1,000? There's going to be 40 deaths per 1,000 live birds, 30 or less than 10. We're going to go with less than 10 because we're expecting it to stay down here again. If we see how it correlates over here on this part of the chart. So a prediction on the data, prediction based on the current trend, is the rate of infant deaths is unlikely to experience sharp declines nor increases in the future. So here, based on this trend, we're saying we don't think it's gonna spike up all of a sudden. You don't have any more data that would suggest that would happen. We're not expecting it to kind of like decrease like drastically. There's not much more for it to decrease. It's kind of at an all-time low. But we are saying like, hey, it could kind of like go up a little bit. It could kind of like go down a little bit. It could kind of just stay the same. And this is kind of the most safest way to say, like, we don't expect to be much changes. And that's fine because we haven't seen drastic changes in the last few years. But if we were kind of like looking, let's say the year was like 1960s and this hadn't happened yet, we would expect there to be a bigger decrease in infant mortality rate in the future, because based on what we see just happening before us, a very sharp decrease. At this point where we are now, like 2020, like we don't really see much change, so we don't expect much of it to change. However, as we know with COVID-19, it kind of just turned our whole world upside down. So never say never. So here it's just very important to look at the trend. What is happening right now? Okay. Next, I want to talk about using like statistics and probability. This is something from the math portion, but there are some math concepts that bleed into science, but they're much easier than like solving for like a x variable. So let's just kind of like get that over with. So we're going to be talking about using statistics and probability. So we're going to be talking first about our measures of central tendency. Okay. With our centers of central tendency, we have the average, which is also called the mean. We have the median. We have the mode. And we have the range. So if we have, and the average is that you add everything together, and you divide the total number of things that are present. The median, it's the number in the middle. The mode is the most frequent number, or most frequent value. And then the range, so, and let's say that I am going to cut a pipe between 4 inches to 5 inches. So I have a range truly of from the beginning to the end. So I have how much space I'm going to deal with, or like what is my, from where to where, my beginning to the end. So you can just get that from subtracting the highest number, the highest value, subtracting that by the lowest value. Okay. So how about we do an example of finding a measure of central tendency? And I think I need to get another piece of paper. Alright, so let's draw another chart. Yeah, we're going to be drawing a lot of charts for this class. So we're going to be looking at annual tornadoes. Annual tornadoes between the year 2000 to 2006 in Goodland, Kansas, Goodland County, Kansas. Okay. So this chart comes from the National Oceanic and Atmospheric Administration. I am saying like where like the charts are coming from because that's very important in science. Like where are you getting your facts from? You can't just pull everything off of like Wikipedia. Okay, so here we have 30, 20, 10, 0, okay. This is a number of tornadoes. Yeah, I made the chart a little bit too big. So we have the year 2000, 2001, 2002. So my range is from the year 2000 to 2006. So 2000, 2001, 2002, 2003, 2004, 2005, and then I finished with 2006. Okay, so in 2000 there was 28. So we saw 28 tornadoes in the year 2000. Let's just shake that in. And then the year 2001, we saw 16 tornadoes. Okay, so there was less tornadoes. In 2002, we saw 12 tornadoes. Okay, 2003, we saw 22. Okay, we saw a spike happen again. So I'm just kind of describing the trends as we're looking at the data. Alright, 2004, we saw 16 again. Hey, exact same number as in 2001. When you see a number come up more than once, it can become the mode. But there can, if like multiple numbers come up multiple times, you're gonna go with the mode that comes most frequently. Then we have 16. Right now we have 18 pop up in 2005. And then in 2006 we have exactly 10 tornadoes. Okay, so let's look at our mean first, our average. So we first have to see our average. We need to add up all the number of tornadoes that there were. So we had 28 plus 16 plus 12 plus 22 plus 16 plus 18 plus 10. And then how many years did this include? It was from 1, 2, 3, 4, 5, 6, 7. Okay. So we're adding all the number of tornadoes over those 7 years. So then if we go ahead and add all of this up, we get 68. Oh, I'm sorry. Let me just go ahead and grab my calculator, because you're going to go ahead and do this in your calculators for the exam as well. Alright. So now I get 28 plus 16 plus 12 plus 22 plus 16 plus 18 plus 10. I get 122. Now I must remember to divide by 7. And I end up with around, más o menos, 17.4. So I get around, let me just round it up to like the nearest whole number. It's just around 17 tornadoes every year in that small county. So just looking at the statistics, and if you wanted to buy a home in that area, you'd probably want to get tornado insurance. If there's 17 tornadoes that happen every year, that's pretty frequent. And you might say like, well, 17, well, there was 28 this other year. So it's like, it still kind of represents, because it's balanced off by the year that there was only 10 tornadoes. You might even say like, well, 17 is way too high of an estimate. Well, it's an average. It's kind of like the in-between, just evenly distributed across the years. That's why the average is just a very good place to kind of find information. Now, like if there was one year where there was like 500 tornadoes in one year, well, it kind of like messes up the rest of the data. Okay, so then if we look at the median would be the value directly in the middle. And then the mode would be 16, because that's value comes up twice. Mode 16, and our range is from the year 2000 to 2006. to just kind of go into like brief overview on how you're going to be dealing with short answer responses. So with the short answer response, you don't get to pick an answer choice. You have to make your own answer. So there's less guessing involved with a short answer response. You can't just go like eeny, meeny, miny, moe. With this, you're going to be given like a little box where you can write your answer in, and you're going to be in order to like properly answer, you have to cite specific evidence. You can't just go general. You have to cite specific data. So you have to cite specific data. And use that data to support a conclusion. Like your conclusion. Or you might get a different kind of question that's asking for you to design a scientific experiment. To test a hypothesis. So you have to cite specific data. Yes, you're not going to have access to Google. You're not going to have access to a lot of other information. You're going to have access to the information they already provide you. You're going to want to use the same information they provide. Do not make other data up. You don't know the source, or even if you do know the source, it's going to be hard for the exam takers to verify it, and it kind of looks like you're going to be making it up. So just go with what they provide. Use what they're kind of already giving you the information. You just have to structure it for them. And then here, with when you're designing the scientific experiment to test a hypothesis, you need to explain the hypothesis. Like, what do you think is going to happen? You also need to have a very logical method on how you're going to collect the data. If you're saying you're just going to collect data willy-nilly, it needs to be a reasonable way that you'll have access to the data. And we'll do an example on this. I'm just kind of going to an overview. And then you need to have also a good way of evaluating the results, like how the results relate to the hypothesis. So you need to have a good hypothesis, or a clear hypothesis. A good design, and then logical method to collect data, and then a reasonable way to evaluate results. here with your clear hypothesis, you're gonna start off and make that your kind of like your thesis statement, if you remember that from writing. Also here, you're gonna want to re-emphasize the facts and other details that you're gonna want to use in your response. There's gonna be like a lot of details in the background information of the experiment. This will be a good time to like highlight or like emphasize that information. That way you can use that information later on. And then if you are going to take the exam at a testing center, they're going to give you like a little whiteboard. That way you can kind of like practice your little response before you go ahead and fill it all in. Oh, by the way, I do want to mention, you can now go ahead and take the exam at home. However, at STC, we kind of are offering for you to come in and take the exam. You just need to go ahead and let us know. It's actually much better if you just go ahead and just take it with us compared at home, because like if your internet goes down or something happens, we don't want you to like lose progress on the exam. Okay, so now we're going to be getting into the next section, which is the life science portion. Alright, we finally got into like all like the course overview. We're done with that. We're going to be talking more about the biology portion. So if you go ahead and watch the little introductory video first, and then we'll watch and then you'll be able to see me lecture on cell structures and functions.